All right, today is lecture 11, and I'll go ahead and share my screen, and we'll talk about what we learned last time. There we are. So today is going to be uncertainty quantification part 2, and then depending on how far we get, it'll also be the start of our discussion of estimation theory. Now, estimation theory, it's going to be a mouthful to say lecture 11, uncertainty quantification part 2 and estimation theory part 1. I'm going to have to find some way to shorten that down before I post these notes. But so to review, uncertainty quantification, which we went over in lecture 10, is trying to answer the question, how well do we know what we know? So we talked about the concept of a random variable, which is a number, which is really a kind of a floating distribution. So you have it kind of this capital Z, which depicts this unknown number, which we can parameterize with certain values. And then the lowercase z is a particular instantiation of that value. And I use the metaphor of like an electron. You know, we know that electrons exist, or particles in general seem to exist as kind of clouds of probability. And then once you take the time to actually measure that particle, you get exact information about it, but that's the particular instantiation of that particle. So there's the cloud of probability, and then there's the actuality. So you could think of the capital letter as the cloud of probability and the lowercase as the actuality. We talked about the concept of mean and of standard deviation or variance. We also talked about skewness and kurtosis. Talked about the uniform distribution and then the Gaussian distribution. Gaussian distributions are fully parameterized by mean and standard deviation. There's no other information that you need to describe them. Central limit theorem was a big part of the reason why Gaussian distributions are so popular. And that is that as you start to stack up more and more and more random events, no matter how they're distributed, the sum total effect of all of them starts to look like a Gaussian. That's called the central limit theorem. There's a fantastic YouTube video on the channel 3 Blue 1 Brown, which talks about that. There are many fantastic YouTube videos on the channel 3 Blue 1 Brown, and I highly recommend you check them out if you feel like any of your math skills could use a bit of a boost. They have some great videos about linear algebra and about statistics, and they have a couple of other fun things, certainly quite a bit. There's a whole video about quaternions, if those seem a little bit odd, and one about some interesting orbital mechanics concepts. Then we start talking about extending random variables up to higher dimensions and creating random vectors, which we would still call RVs. It's going to be the same acronym, random vectors. And so mu becomes a vector, and the variance, or in this case, the covariance, becomes a matrix, which describes the variance of each element and then the covariance of each element with each other element. That's kind of the idea. We talked about the correlation coefficient, and then we talked about this idea of creating k-sigma error ellipsoids. And so this is kind of where we finished towards the end of our last lecture. It's where we're going to pick up today. And so the idea here is we know for a particular random variable, once we know, or a particular random vector, once we know its p, the covariance, we can actually describe these error ellipsoids. And so in the 1D case, you could think of the 1 sigma bounds as just being everything between 1 sigma, positive 1 sigma, and negative 1 sigma of mu. That's the idea. And then there's the 2 sigma bounds and the 3 sigma bounds. Now, those are linear kind of stretches on the timeline, so to speak, in the 1D case. In the 2D case, they become an ellipse. And then in the 3D case, they become an ellipsoid. And so I use the idea that in the 2D case, you're kind of constructing a dartboard. It's like you've got your mean, you've got the bullseye that you're kind of expecting that it is. But then with greater and greater degrees of certainty, you're like, well, maybe I can't hit, the bullseye, but I'm really pretty sure I'm going to at least hit the dartboard and not have to spackle over the walls in my apartment, that kind of thing. And then similarly in 3D, you have these shapes, which I refer to as like Russian nesting dolls, essentially. So you've got a 1 sigma ellipsoid inside of a 2 sigma ellipsoid inside of a 3 sigma ellipsoid. So this is everything that we discussed last time. And the reason I wanted to do such a thorough review of last time is that the very first concept today is kind of an immediate follow-on from the very last concept last time. So I wanted to make sure that we were nice and fresh on this material. And so I wanted to discuss, you might be familiar with the idea, and actually we're going to introduce this in a second with numbers, that if we go back to the 1 sigma idea, oh, went too far, that's matrix vector calculus. If we go to lecture 10, within 1 sigma of mu is something like 68% of the distribution. So if you know the average height of a group of people and then the standard deviation, 68% of the population are within one standard deviation of the average height, right? That sort of thing. Anything that's normally distributed would follow this idea. And then 2 sigma is 95% approximately, and then 3 sigma is greater than 99%. So everything that exists outside of 3 sigma is less than 1% of the population, of the distribution, of the PDF, the area under the curve, whatever you want to call it. The thing is, that is not true in higher dimensions. And I want to talk about why that's the case. Just to kind of understand briefly why we don't carry around the same certainty about 3 sigma in 3-dimensional space that we do in 2-dimensional space. So before proceeding, we should consider how much of a distribution the K sigma bound contains. Okay, so we're familiar with this. For a 1-dimensional Gaussian of the sort that we are familiar with, we have 68.3% of the distribution lies between mu minus sigma and mu plus sigma. I'm going to try to clear up that word and. There we go. And then we also know that 95.4% of the population lies within mu minus 2 sigma and mu plus 2 sigma. And we also know that 99.7% lies between mu minus 3 sigma and mu plus 3 sigma. Okay. So you may recall this from statistics, but this is only true for the 1D case. So for a 2D Gaussian, this is just FYI, for a 2D Gaussian, 39.3% of the distribution lies between, actually, we can't really say between, more like lies within the 1 sigma ellipse. So we're carrying less confidence in this case. And actually, it's even more extreme. For a 3D Gaussian, it is 19.7. So now only 20% of the distribution falls within the 1 sigma ellipsoid. Okay, interesting. So why is this the case? And why do we care about this? Well, why do we care about this is pretty straightforward. If we're going to tell our manager or our boss, we say, well, we now know the position of the spacecraft and the covariance of the spacecraft's position, which means we know the 3 sigma covariance ellipsoid, that we're a 99.7% chance that we're in there somewhere. It's like wrong. That's actually not the case. It's not 99.7. because it's a 3D ellipsoid. If it was a 1D Gaussian, it would be 99.7. So just we want to temper our expectations for exactly how sure we are. I'm not necessarily going to go into the math of where this comes from or the exact numbers that you need. I just want this kind of an FYI that there is less certainty at these higher dimensions. I'm going to draw a picture to describe why this is the case. And then I'm going to take a break and restart OneNote because OneNote's been giving me some troubles here. So I just want to build an intuitive sense for why this is the case. So why is this? Okay. So let's look at a distribution that looks like this. So we've got an x-axis and a y-axis. Let's pretend I can draw straighter lines than that. Here's this way, and then this way. That'll do. And let's say this is Z1 and this is Z2. And let's say that there is some mean, and then we'll say that there is some, we'll use maybe like cyan again, kind of like there, like a sky blue. Sky blue is nice. Let's say that there is some 1 sigma distribution. I'm doing my best to draw a circle here. We're going to assume that there's no correlation between Z1 and Z2, which means that our 1 sigma ellipse is actually a circle. And then maybe we'll draw to keep the color code from last time. What did I do? I did blue on the inside and then green. I'm not going to bother with the 3 sigma. I'm just going to draw 1 sigma, 2 sigma. Actually, wait, green. There we go. Not exactly to scale, but you get the idea. Go. And maybe this just barely touches there. Good enough. We're going to pretend that these are concentric circles. All right. Oh, wow. Okay. Clean this up. Okay. So now here's the idea I want to get across. Let's say that we've got these dotted lines coming down. And let's be abundantly clear, go back to sky blue for a second, that this is 1 sigma. And then that this is 2 sigma. I want to be abundantly clear about that. Okay. So now we know that this distance here, for this position, is going to be mu1, the average along the Z1 direction. And then if we kind of march our way over here and look at the top and the bottom. Okay. I realize I've painted myself into a corner with this here. Bear with me. Gonna have to extend the y-axis a little bit here. Just because there's not enough room anymore. There we go. So I'm trying to get apart this idea here. There we go. This is still the Z2 direction. Okay. So let's say then this is mu2, and that this distance here is the 1 sigma in 1 dimension. So we're saying, okay, of the entire distribution, 68.3% exists between here and here, and then also this is 1 sigma. So 68.3% of the distribution lies between here and here. But now we're looking at higher dimensions. So the real question is, if you were to kind of extend this out, right? Get the idea here. We're including the rest of the distribution in the other dimensions, if that were to make sense. So you could think of it this way. The 1 sigma in the Z1 case includes the entire distribution along the Z2 case between plus and minus 1 sigma of mu1. So you're getting not just the blue circle, but you're getting the areas outside the blue circle, you're getting the areas in the green and then the red. So you're getting this entire rectangle. That is 68.3%. And then similarly, if we look at it horizontally, you've got like another rectangle from plus to minus sigma of mu2. That is 68.3%. but the intersection, it's almost like a Venn diagram, right? The intersection of this 68.3 and this 68.3 is less than 68.3. And then as you continue in higher and higher dimensions, it gets less and less and less likely. So I just want to temper your expectations here for the confidence that 1 sigma and 2 sigma and 3 sigma actually carry with them. Still in practice, I'll see the 3 sigma position and velocity covariance ellipsoids. We'll still typically go to 3 sigma, but with the understanding that we're no longer capturing 99.7%, we're capturing a little bit less. Anyway, questions on that? And while we pause, I'm just going to restart OneNote really quickly here. See if it plays any more nicely with me. All right, so moving on. Next topic I want to talk about, one of my favorites, and I think after today it's going to be one of your favorites too, is going to be eigendecomposition. So I mentioned, there we go, eigendecomposition. So we're going to be using eigendecomposition as a tool to better understand the covariance matrix and the covariance ellipses and ellipsoids. And eigendecomposition was something that I think I mentioned last time I found pretty strange and arcane the first time I learned it, and then also the second time I learned it, and then the third time, and so on and so forth. But by about the 10th time I saw it, it finally started to click, and that was when I was learning this material for the first time. And so I'm hoping that things start to click a little bit for y'all as well. So I'm going to talk about eigendecomposition and how we can use it to express or better describe the positions of, or the kind of covariance of some unknown random variable. And then we're actually going to have an exercise today. I feel like an in-class exercise would be a good way to kind of shake off the cobwebs when it comes to eigendecomposition. So I hope you all have you can either open up MATLAB or Python in a second window, or you can get out a piece of paper. We'll get to the exercise in a little bit, and it's not going to take too terribly long. Just thought we'd shake things up a little bit today. So we'll start with an example, just so you understand what we're talking about. Given, this is the question, given an n by n covariance matrix P, how does one plot or interpret this? Okay, so let's consider an example in nice, friendly 2 dimensions. Consider the 2D example. P is equal to 9, 0, 0, 4. Nice and straightforward. In this case, we can determine some things by inspection. Okay. So first of all, there is no Z1 to Z2 correlation. Okay, why is that? Well, because we know that the diagonal elements of the covariance matrix describe the covariance, or in this case, just the variance of each term with itself. So 9 is something to do with how little we understand Z1, 4 is something to do with how little we understand Z2, but then the off-diagonal elements describe the relationship between them. And we should mention that it's guaranteed to be symmetric. So as soon as I wrote a 0 here, we knew it was going to be a 0 on the bottom left. Now, 0 means there is no covariance between Z1 and Z2, meaning there's no correlation. And that means if we were going to plot P, then the ellipse will align with the Z1, Z2 axis, meaning there is no rotation to this covariance matrix. Okay. We also know sigma 1, which is just the square root of 9, which is 3. And similarly, sigma 2 is the square root of 4, which is 2. So that actually gives us all the information we need if we wanted to plot, and I'm going to go back to lecture 10 for a second, wanted to plot something like this, where we have our 1 sigma, 2 sigma, 3 sigma error ellipsoid in the Z1, Z2 space, we can do that. We can better understand what's going on. So why don't we go for it? So, pardon my art skills. I'm actually going to try to draw something to scale here. So, buckle up, everybody. Let's see how well this goes. So we're going to have vertical axis, horizontal axis, and this is going to be Z2, and this is going to be Z1. I'm going to do tick marks. We're going to do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 6. 1, 2, 3, 4. 1, 2, 3, 4. That'll do. So now, here's what we know. Let's do 1 sigma to start. Go back to sky blue. I'm going to maintain this color code. We know that Z1 has an uncertainty of 3, right? 1 sigma is 3. So we're going to be between here and here along the Z1 axis. Did I lose something? There we go. Here and there. And then along the Z2 axis, the uncertainty is 2. So we're going to be between here and here. So I'm going to do my best to kind of spline between those to produce an ellipse. Go. Somehow I lost that tick mark. Not quite sure how that happened. There we go. There's my best 1 sigma error ellipsoid. And now, if you can believe it, it's just as simple to do 2 sigma. So 2 sigma is going to be between 6 and -6 and 4 and -4. And so if I do my best to kind of spline between those, bear with me here. See, this is where I'm going to give myself some credit, because I could have just whipped this up in like PowerPoint art and it would look perfect, but I chose to try my best to hand draw this because I knew that y'all were going to be hand drawing this as well. Definitely not because I was too lazy to put this together in PowerPoint. That's not what's going on. There we go. There's 2 sigma. And I'm starting to regret not using an ellipse drawing tool, but you get the idea, right? So this is how we can understand this covariance ellipsoid, 9004. The fact that it zeros along the off diagonal means that everything is nicely oriented. It's nicely aligned with the Z1, Z2 axis. It could have been cranked up and to the left or up and to the right, like we see here, but it wasn't. And then the 9 gives us information about the uncertainty along Z1. The 4 gives us information about the uncertainty along Z2. The fact that 9 is greater than 4 means that the covariance ellipse is going to be wider than it is tall. Okay, I think we've beaten this to death. So now, here's the big question, how do we handle P, or how do we plot the uncertainty when P has off diagonal elements? Because I really like doing this, and I could, don't really love the idea of now there's off diagonal elements. How do we handle that? And the answer is we can cheat and force a matrix that has off diagonal elements into one that does not have off diagonal elements. And the way that we do that is with something called eigendecomposition. And here's all it's saying, right? This is when eigendecomposition really clicked for me. What we're doing is we're taking a matrix and we're expressing it in its own principal frame. And in its principal frame, there are no off-diagonal elements. It's going to be a diagonal vector. And so the eigenvalues are the members of that diagonal matrix, and the eigenvectors actually describe an attitude transformation matrix to get you from your initial orientation to the final orientation. And so that is what we're going to cover in the next section here. And so we're going to have a little example coming up. There we are. Okay, so eigendecomposition, which I'm going to start to kind of shorten that to eigendecomp, will tell us the covariance, or in this case, the variance in the principal frame and those are the eigenvalues, as well as a rotation, or we're going to call it a direction cosine matrix, just to be clear, because it's not a rotation matrix, as well as a direction cosine matrix from the initial frame, whatever that is, to the principal frame. And those are your eigenvectors. Okay, first of all, let's convince ourselves of this, right? So let's convince ourselves of this before we move on. You can just take it by fiat, or we can do a proof. Let's convince ourselves of this. So let's take some vector z, and we'll say, okay, z prime is equal to tz. Okay. So apologies, I'm going to be fast and loose. Rather than using frames, I'm just going to say prime is just in some new frame. So you've got z original. After you apply a attitude transformation matrix or a direction cosine matrix t to it, you get z prime. Okay. T prime is the expected value of z prime minus mu prime, and then z prime minus mu prime transpose. That just comes from the definition of the covariance matrix. So then z prime minus mu prime is just t times z minus mu. So what we're really saying is that p prime, so p in some new frame, is the expected value of t times z minus mu. Let's put little vector heads over those, times z minus mu transpose t transpose. Okay? Or remember, the expected value operator only acts on the things that are stochastic, right? So t is a known value in this case. So we're just going to say p prime is equal to t expected value of z minus mu transpose t transpose. So we can move the attitude transformation matrix outside, but now all of this, the expected value of z minus mu transpose, is just p in the original frame. So what I'm saying is p prime, the covariance matrix in some new frame, is t transpose. Okay. So if t takes us from the original frame to whatever this prime frame is, then this is the way we can understand how to go from the original covariance to the new covariance. Right? So all we're proving to ourselves is that's the way we handle that. Now it's also worth mentioning what is not the case. It is not the case that p prime is equal to tp, or that p prime is equal to pt transpose. That's not how that works, right? When you have a matrix, you don't multiply by a direction cosine matrix once. You actually have to multiply it on both ends. It's kind of sandwiched, if you will. That's an important concept. Okay, so now, moving on, let's actually go back to the idea of eigendecomposition. So let's set up our eigenvalue eigenvector problem. So P, and we're just going to use UI. Now I forget, did we set up a, oh, it's been a minute. Trying to remember how we had this set up. In the attitude representations, I want to use this. I like to be self-consistent with my notations. Just bear with me for a second. Um, attitude representations. It was in the lecture 6, I believe. We talked about the eigen angle and eigen axis, and we set up a, yeah, okay, I used E then, and specifically E with a hat, where E was the Euler axis. Um, mm, no, I'm just gonna throw that out the window and use U. Right after I said I was gonna try to be consistent. Just bear with me for a little bit. We're gonna use U today. It's fine. So PU, something smells, is equal to lambda I U I. So in this case, U is the vector, which is going to be a unit vector in this case. And this is the characteristic equation of any eigenvector eigenvalue problem, right? So P times some vector is the same as just scaling it by some value, right? In this case, we should mention, because the scale of eigenvectors are unimportant, we can choose them to be unit vectors. Okay, just being clear about that. So if I was going to set up a larger system of equations, it would look like this, right? P times U1, U2, all the way to UN is equal to, it's going to look like this. U1, U2, all the way to UN times some matrix, which is a diagonal matrix consisting of lambda 1, lambda 2, all the way down to lambda n, with all zeros on the off-diagonal elements. Okay? All we're doing is taking the exact same idea and just scaling it up to a higher dimension. So I'm going to define this stack of all of these eigenvectors kind of sandwiched together as capital U, which is going to be the exact same thing over here. And I'm also going to define this matrix of eigenvalues as capital lambda, which capital lambda looks like that. So what I'm saying here is P U is equal to U lambda. Okay. Hopefully you would agree that I could just as easily say P is equal to U lambda U inverse, or U inverse EU is equal to lambda. You can think of it either way. I'm going to clean up that lambda in a second here. So PU is equal to U lambda. You can take it in either direction, but now what we're noticing is this U inverse PU is starting to look a tiny bit like P prime is equal to TP transpose, and we understand that when we're dealing with a orthonormal matrix, the transpose and the inverse are actually the same thing. So let's make a few notes here. Since P is symmetric, we know U is an orthogonal matrix. We also enforced that the columns of U are unit vectors. Therefore, this is an orthonormal matrix. It is an attitude transformation matrix. This is the key takeaway from today's discussion of eigendecomposition. The eigenvectors lined up is an attitude transformation matrix from the principal frame back to the original frame. Maybe y'all knew that already. I feel like the first time that really clicked for me was when I heard it in this context. And so I feel like that will hopefully help us understand. It's basically T, right? Attitude transformation matrix. So let's try to clean this up a little bit, right? So I'm going to say that P prime is the principal frame. And P is in just the initial frame. Okay. So what I want to set up is this. U transpose PU is equal to P prime, which is lambda, right? So P prime takes the role of lambda. Lambda is all of the eigenvalues lined up in a diagonal matrix. That's the diagonal matrix that we're after. That is the covariance in its own principal frame. Okay. So then remember the way that we decided to set this up. We decided to say that, here, I'm going to clean this up for a second. P prime is equal to T transpose. By this same definition, I'm going to kind of clean this up. So we're going back up here. This means that P is equal to T transpose goes there. There we go. So I want to get this idea across that T, in this case, is U transpose. So if we say, okay, some vector Z prime is some vector Z multiplied by an attitude transformation matrix, that means that in our case, T takes the form of U transpose. And so we can say, okay, T transpose is equal to lambda, which is P prime. Okay, so here's the key takeaways, right? The eigenvalue matrix is equal to the covariance matrix in its principal frame. And the eigenvector matrix, I want to make sure I get this straight. The eigenvector matrix is the maps us from the eigen. Here we go. I have a nasty habit of getting this backwards, so I want to make sure I get this straight. Is T from principal to initial? That's what I'm trying to get after here. So you can think of it this way, right? P, the original eigenvalue, or the original covariance matrix is in this case U lambda U transpose. That's what I'm getting after. Where U is the eigenvector matrix. And, well, exactly backwards. Sorry, strike that, reverse it. Lambda is the eigenvalue matrix. U is the eigenvector matrix. There we go. Yeah, I have a nasty habit of getting those backwards, which is like, it's a 50-50 shot. So getting it backwards is a complete failure. So I want to make sure that I don't lead you down the wrong path. That's the key. Like, this is kind of the key takeaway here. Key is this. This is our breakdown. Okay. And so with that, it follows that we could do the following. If we had some matrix, I'm going to scroll back down in a minute, so just bear with me. If we had some covariance matrix P that wasn't diagonal, we could do eigendecomposition on it to produce a kind of alternate covariance matrix P in its own principal axis frame that, pardon me, is diagonal. And we can plot it in that frame. And then the attitude transformation matrix, which is the eigenvalues and eigenvectors all stacked together, or sorry, the eigenvectors stacked side by side, gives us the rotation between the two different frames. And so that's what I'm going to challenge y'all to do. So I'm going to give you an example, and I'm going to give you let's do, let's try 10 minutes to attempt it. And if people feel like they need a little bit more time, we can do that. But with a blank sheet of paper and or MATLAB or Python open on another terminal, try this. Let's use a numerical example. To drive this point home. So let's say that P is equal to, here it comes, 3.25, 1.229, 1.229 again, because we know it's going to be symmetric, and 1.75. Okay. Your goal is to find the eigenvalue matrix and the eigenvector matrix. So we're going to do eigendecomposition on P, then draw P. There's your goal. I'm going to give everybody 10 minutes to do this, and then we're going to take a 5-minute break. So it's going to be kind of a combination of break and attempt. So it's about 6:15, 6:49 now. Let's do back at 7:04. So if you feel like taking a bathroom break or something first, you're certainly welcome to. If you want to spend a little bit more time chewing on this, you're certainly welcome to. I'm going to stick around for the whole break in case anybody has any questions. Otherwise, see what you can manage with that numerical example.
Hey, Paul.
Yep, what's going on?
Can you is it okay? Can you scroll up when it says eigenmatrix equals to was it principal force or like the
Uh,
little P and yeah. All right.
yep, eigenvalue matrix is P in its principal frame.
All right.
I
Thank you.
realize that my handwriting is kind of a bottleneck on this operation. Oops, not what I was attempting. There we go. All right, I reckon it's probably a pretty good time to start back up again. All right. So I'm guessing that a lot of you are preferential to MATLAB. Maybe some of you are Python folks. Some of you might not prefer either of those two. And some of you might have gone on about trying to sort this out by hand. So I'm just curious. I'm gonna stop sharing for a minute. I just want to get a poll going. I assume everybody's back. Just throw your hand up if your preference is to do eigendecomposition in MATLAB. I want to see how many people that is. All right, decent chunk. Oh, all right, cool. All right, so we'll do hands down. And now I'm just curious, who finds it easiest to use Python? All right, love it, love it. And then who prefers to do it using software that's not either of those that I just didn't think about? Like maybe, I don't know, C or something else. All right. Whose preference is handwritten? Anybody still like to do it out long ways? All right, cool. I'm just curious where people's how everybody feels about that. Okay, cool. So it looks like a lot of people like the MATLAB way, and I'm not trying to marginalize people who don't like the MATLAB way, but I'm going to do a quick demo. I assume that people know, well, not necessarily a demo, but this is the documentation for the MATLAB command, which I guess is probably people have already seen this because this is what y'all just did. But so the command is eig, and so the kind of best way to do it is vd equals eig of a, where you're going to get v is so d is the diagonal matrix of eigenvalues, and then v is the eigenvectors. That's typically the way that's set up. Vd equals eig of a. So that's my preferred way of doing this. You could always do it any other way, but what you should get, and we'll start to kind of follow through the procedure here, and we'll see how close people got. All right. And then after this, we'll move on to a completely different topic here. So I'm also going to erase this. That was your exercise. So first, we will find eigenvalues and eigenvectors using, the equation looks like this. The determinant of lambda I minus p equals 0. That's how you would start to do it out long ways, or the MATLAB eig command. And I imagine that in NumPy or NumPy, it's very similar, but np.eig or something to that effect. So what we will find, hopefully people got this, this gives us the lambda matrix is 4 and 1. Hopefully people got that. 4 and 1. And then similarly, the U matrix, the way I got it, looks like this. 0.866, 0.5, negative 0.5, and 0.866. That's what I got. Somebody correct me if they got something different. But now this should look a little bit familiar. Does anybody know what is going on with this matrix? These numbers, especially that number 0.866, ought to look really familiar from trigonometry. Anybody want to take a crack at that?
Is that the one that's like square root 3/2?
It is, and it's also the cosine of what angle?
Oh man, I forgot.
That's right. You were
Is it
absolutely right that it's root 3/2.
is it cosine 30 degrees?
Yep, that's exactly right. Cosine of 30 degrees is 0.866. 0.5 is the sine of 30 degrees. So this is the negative sine of 30. This is the sine of 30 again. And then this is cosine of 30 degrees. There we are. And so t, which takes us from the, so how do I want to set this up? Let's think of it this way. P is u lambda u transpose, or we could think of it the other way, that the original matrix P, so it's kind of two ways. I'd like to think of it as, well, we'll start by drawing it out this way. I'm overthinking this. So clearly, if we were to draw the eigen or the covariance matrix just using the eigenvalues, we would have something set up like this. And I'm going to do this a little bit differently, right? Just a quick sketch. We know that what this would give us is something like this, right? The first term, square root of 4 is 2, so it'll be 1, 2, and then the square root of 1 is 1. So we know that our covariance, we'll put this back to sky blue, would look a little bit like this. Wow, all right, I could definitely do better than that. One more try. Goes from -2, -1, +2, +1. Maybe we'll try making 2 laps, and that'll clean it up a little bit. It looks a bit better. And then we can also go through and draw this just a little bit larger, like so. Get the idea. So this is the covariance ellipsoid, or the covariance ellipse in the U1, U2 frame. You think of it that way, right? So this is the covariance in the principal frame. What I'm curious about is the relationship from the initial frame to the principal frame. So whatever our starting frame was, in order to get from the initial frame to the principal frame, that is U transpose, which is cosine 30, sine of 30, negative sine of 30, cosine of 30. So what that means is the relationship between the initial frame and the principal frame is a 30-degree rotation about the z-axis, or the out of plane or out of page axis, that's kind of the idea here. So this direction cosine matrix is simple enough as to be recognizable. And what this is saying is that if this is the true frame, so this is the original kind of Z1, Z2 axis, that the relationship between that frame and the new frame, maybe I'll use some other color, use purple or something, is a 30-degree rotation. That's a lot more than 30. Let's back off a little bit on that. That's close enough to 30. Where now this is the U1 direction, this is the U2 direction, and this is 30 degrees. And the way we've drawn this now, actually we'll do this. Let's do tick marks at 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, and 1, 2. I guess there's no way to draw this so that I don't just annihilate that thing where I say 30 degrees, but you get the idea. So now we know what the covariance matrix looks like in the principal frame. So we're just going to kind of take this drawing and just kind of scooch it up 30 degrees. Is basically the idea. Try to kind of clean that up a little bit. Wow, somehow worse. But on average, it looks still worse. Cool. We're just gonna move forward. All right. So then we have 2 sigma like this. There we go. This is 2 sigma. Go back to sky blue. This is 1 sigma. All right. So I'm going to guess that folks in general made it at least as far as the eigen decomposition. They got lambda and they got u. I'm going to guess that folks maybe even got this far as the drawing the covariance in the principal frame, which is great. The last step, you know what? While I'm kind of talking and making filler noises, I'm just going to try one more time and making this look a little bit prettier because this is going in the notes that I send out. I'm going to try a little bit harder. This was the final step, and I'm not sure how many people made it this far, but this is kind of what I was looking for. Was all right. We can actually find from the eigenvector matrix the rotation from the initial frame to the principal axis frame. And I think that is going to be the key thing to take away from this, right? Is to understand, and this is something that I don't just teach, but I use when the time comes to do covariance analysis. You will frequently get the covariance in, you know, the local frame or whatever frame you've chosen to do your analysis in. But then you might be wondering, well, what about my uncertainty in the moon-centered, moon-fixed frame or the Earth-centered inertial frame or some other frame transfer? So you want to be able to do this sort of frame transformation. And that's essentially it. So that concludes my discussion on eigendecomposition, and also concludes our discussion of uncertainty quantification. So moving forward, it's going to be a different topic. So questions on that, or are we good to move on to the next thing?
I have a quick question.
Yeah, I have an answer for you.
Oh, yeah, yeah. I don't know how, but when I was doing my MATLAB, you plugging in, just using MATLAB to find the eigenvectors and the matrix, eigenvalue matrix, eigenvector matrix, I'm like getting numbers not exactly 4 and 1, or exactly 0.5, 0.866.
Oh, yeah, I'm gonna guess that there's some numerical stuff going on. Was it like 3.999 and 4, well, like, well, how different are we?
It was like 1.0602 and 3.9398.
Yeah, no, I think that comes down to me not adding. That's probably my fault. So the problem is, yeah, it would be up here. I really should have probably included a few more. So I guess, yeah, some rounding is in order to kind of make this make sense. My apologies. But yeah, I don't think that you're wrong because I remember running into something similar when I coded this up for myself. Um, but yeah, apart from the numerical stuff, did the concept all click though? That's good.
Yeah, it clicks. I think, yeah, I think it should click because do you like when I was also doing as well, the 4 and 1 also switch place as well? Is
That's okay. That's actually
that's
totally
okay?
fine because what'll happen
Okay.
is if you switch those out, let me erase this too. I like to have the first one in the top left, which is fine, and it just means you would change the order of your eigenvector matrix. Because now, if you switch the 1 and the 4, it's also going to switch around your u, which is
Yeah.
fine. What would then happen is you're saying that the u1 direction is not 30 degrees away from z1, but 120 degrees away from Z1. And so your resulting
Oh,
U matrix would be a trans. So it's kind of the same idea, right? You could either say that U1 is 30 degrees off, or you could define U1 as this one and say that it's 120 degrees off.
okay.
Same idea.
That makes perfect a lot of sense.
Good.
All right.
Sometimes when I say stuff, it makes sense. I like to celebrate those times. Okay.
All right. Thank you
Uh,
so much.
yeah, other questions, or are we good to move forward? I want to get to the point before we leave today, and I recognize that it's like getting down to 6:20 already. Really want to get to the point where you could start homework 1 because as of right now we still haven't gone over enough stuff to start homework 1. So I want to push, even if it takes us a little bit past how long I would normally want to go. I want to push to finish up our discussion of something called least squares, which is going to require burning through about 2 more pages of stuff. So bear with me. And as a matter of fact, I might even set this up as a new lecture altogether. So maybe I'll call this lecture 12. And then I'm not trying to panic you and be like, we have another hour of stuff to do. We do not have another hour of stuff to do. But I want to say this is estimation theory part 1. And I'll post 2 different sets of notes. I just think it's going to be cleaner if we break it up this way. So today was technically 2 lectures. Okay, so we're going to talk about something called estimation theory. And today we're ultimately going to land on something called least squares, which I hope that we've seen before, but that you might kind of see today in a new way. So estimation theory is a branch of statistics that seeks to estimate the value of a random vector or RV from a set of noisy measurements that are functionally related to the random vector of interest. So I got to hit you with a textbook definition every once in a while. Estimation theory is a branch of statistics that seeks to estimate the value of a random vector from a set of noisy measurements that are functionally related to the RV of interest. So the takeaway here is the last 2 lectures, or the last 2 concepts, uncertainty quantification, parts 1 and 2, are talking about random vectors and random variables as things that we have a general understanding of how it's distributed, but we don't fully understand what the number is. It's got an expected value, it's got a covariance. We talked about how we can model those, how we can better understand those and use those as tools. Now we're going to talk about how to find out what they are. So starting with measurements and trying to find out what our random vector is. So this is kind of the foundation of the rest of estimation. And I would say estimation theory techniques, or maybe I'll write it this way, techniques from estimation theory are often used by the navigation community to estimate spacecraft states and other parameters of interest. Okay, so, and this should sound a little bit familiar. Matter of fact, maybe we're kind of tickling your memory a little bit. Estimate the state of a spacecraft and other parameters of interest is, well, I have to go back to my slides, but that's the definition of navigation that we gave in the first lecture. Navigation is estimating the state, position, velocity, attitude of a spacecraft, as well as other parameters of interest, given some noisy measurements that we have, right? So we have instruments that give us measurements, and someone needs to sit down and do the math to determine what the position, velocity, attitude is, and that someone is us. And that's what we're going to be doing. So to begin, consider the linear measurement model and we're going to say first without noise. Yi is equal to Hix, where x is a vector, x is the state whatever that is. We're going to leave that out for now. It's going to say it is the state, could be position, could be velocity, could be something completely different, could be the state of a nuclear power plant, information about the pressure and different, whatever it is, state for now. And then yi is the measurement. And as written, yi is a perfect measurement. And then with noise, we would write it this way. Yi with a little hat on it, it's meant to be like a tilde hat on it, is equal to hix plus nu I. I should be clear. This is the Greek letter nu, not B. That's my best attempt. And those are going to start to look, the faster I go, the more kind of sloppy that's going to look. Nu as in noise, right? So it's the Greek letter N is noise. And we're also going to say that nu I is distributed as, well, it's Gaussian with 0 mean and sigma I squared is the variance. So I'll explain what that means just now, actually. For the time being, we will model the noise as 0 mean, Gaussian, white noise, having a known standard deviation sigma I. Okay, so now we're going to start considering systems of equations, right? If we have multiple measurements, we can stack these systems of equations, which I'll abbreviate to sys of ec, into vectors. Okay, so let's say y1 with a little hat all the way to yn with a little hat. That's now a vector. And that's going to be equal to h1 all the way to hn. X is just still x. And then this is going to be nu 1 all the way to nu n. There we go. Or we'll do shorthand because there's no way I'm going to keep writing that. This is going to get a little bit tricky. Y is going to have a hat to show that it's a vector and then a different hat to show that it's noisy. That's going to be my notation. Y with the vector and then also the noise is equal to, I'm just going to call this whole thing H, which is a matrix, times X plus nu, which also gets a little vector hat. And in this case, nu as a vector hat is now a random vector, which is distributed as, again, Gaussian with 0 mean and with a covariance of R. So I'm going to say really quick before we move on, R is the measurement noise, or just the measurement covariance matrix, which we will return to this idea, but it's important to mention this is defined as the expected value of nu transpose. So R gives us information about the noise in our measurements, or not necessarily gives us, because typically R is something that you would need to go find, right? R is the information about the uncertainty in your measurements. Okay, so question to all of us, how do we go about solving a problem? So here's kind of an open question. How to solve for the state X given your noisy measurements, all nice and stacked for you, and H, which we're going to refer to as the measurement sensitivity matrix. So this is just purely a math problem, right? How do we go about solving for X given Y and H? And this is an open, not rhetorical question, so I'll take whoever feels like answering that. We know that if we have AX equals B, it'll look a little bit like that, right? Wouldn't X be A inverse B?
So would you just subtract nu, so then it's y minus nu, and then like put h to the other side, so it's h to the -1?
Ah, but the tricky part is we don't know what the noise is. So
Oh,
we're modeling the noise as some random variable that we don't know what it is. We understand how it's distributed, kind of. We think we know how it's distributed. We're kind of forced to ignore nu in this case. But so if we did that, then it would kind of look like, just pretending that it's not there, y equals hx. So that would mean that h inverse y is equal to x. But then we run into a problem, which is that h is a matrix, which in general is going to be longer than it is wide. It's not a square matrix. And in order to invert a matrix, it needs to be square. So we run into a problem there as well. And while we're just stacking on top problems on top of problems, another problem for us. So I'm just going to kind of write these all out so we're clear on what the problems are. There does not exist, this is the notation for that, backwards E with a slash through it. There does not exist an estimate of X such that the Y that we get out of it is equal to the noisy measurements. We can't recreate our noisy measurements by guessing at X. That doesn't exist. And, well, that's basically it. The other thing is that H is not invertible. All right. So one option is pretty much what we just outlined. So thank you to Italia. One option is this. Is to hope noise isn't a huge issue and solve X is equal to H with a little dagger, Y, where this is what's called the Moore-Penrose pseudo-inverse. You might say, okay, Paul, we can't invert H, but I know that there's the Moore-Penrose pseudo-inverse. Why don't we just do that? Another option is something we're going to talk about next, which some of you might have bumped into before. It's called least squares. And what I'm trying to go over is to show, we will see, that these are the same thing. So the simplest possible solution to a linear estimation problem with noise on our measurements that we don't fully understand is to take the Moore-Penrose pseudo-inverse of the measurement sensitivity matrix and then solve X is equal to H pseudo-inverse Y, which is the same thing as least squares. And we're going to see that in a minute. So I say that, I recognize we're going a little bit long today. I've got one more page of stuff to burn through, which should take about another 5-10 minutes. It's important to me that y'all at least have the tools to start homework 1, because we're getting pretty far behind on the lecture notes, and that's partially my fault, pretty much entirely my fault. But I really want to go over least squares today. We will review this tomorrow, so if y'all have somewhere to be, you're certainly, totally, you're dismissed. I'm going to keep going for about another 10 minutes, and then I will post the notes and the recording, and then we will pick up on this next time. But for everybody who is good to continue, we're going to burn through an introduction to least squares. So least squares. All right. So we're going to start off with a problem that looks like this. Y with a little hat on it, which is an m/1 vector, is equal to our measurement sensitivity matrix, which is an n/n matrix, times our state, which is an n/1. So M Mike is the number of measurements, and N November is the number of states. And then, oh, I'm sorry, not equals, but plus our noise nu, which by necessity is also Mike by 1. And we're going to have some assumptions that go along with this. Assumptions. All right. First of all, M is greater than N, which means we have more equations than unknowns, or we have an overdetermined system. So we're going to need more measurements than there are unknowns. We're also going to assume that the measurement sensitivity matrix H is full rank. If it becomes singular or rank deficient, then things start to fall apart very quickly. So here's what we're after. We seek a solution for X such that Hx is as close to the noisy measurements as possible. That's what we're after. We will donate, sorry, that's me. I'm tired. We will denote. There we go. Same letters, just rearranged. We will denote this optimal estimate as X star. So let's consider the case that's meant to be an N as in November. Let's consider the case when Mike equals 3 and November equals 2. So that would look like this. Your noisy measurements is equal to H1, H2 stacked. This is going to be a 3x2 times X1, X2 is going to be a 2x1. This is going to be a 3x1. Right? So I want to draw kind of a picture of what we're after here. So let's assume that H1 and H2, the columns of our measurement sensitivity matrix, are two vectors floating out in space. Okay, so we're going to say there's one vector here, and then another vector here. And now, by definition, those two vectors define a plane, H1 and H2. And you can think of X1 and X2 almost as like Etch-a-Sketch knobs. So you've got some amount in the H2 direction, some amount in the H1 direction. Well, then you're going to get some point right here, right? X1 and X2 are kind of instructions for where to go on the H1, H2 plane. But as drawn, there is absolutely no way for X1 and X2 to ever get you somewhere that isn't in the H1, H2 plane. Okay, cool. Now let's draw a vector that's not in the H1, H2 plane. So I'm going to say that this vector y is not in the plane. And that's not super obvious the way I've drawn it, so I'm going to try to kind of tidy this up a little bit. Let's say that y projects, so I'm going to use, let's go back to sky blue. It projects to a vector that is in the h1, h2 plane. And there's the projection. So you can think of y as this orange vector, which casts a shadow, and the shadow is the blue vector. And the blue vector is in the h1, h2 plane. So the blue vector would look like this. h1, x1 plus h2, x2, where this is our best guess, right? And this projection right here would be written as y minus h x star. So it's the remainder, right? You've got the projection of the orange vector into the plane, that gives you the blue vector. The remainder is this component that is not in the plane, and that's going to be that dotted line. When I'm thinking of this, I think of the orange line as describing a baseball, and then the blue as the catcher, or I guess field. There's glove. I'm going to erase this in a second so nobody ever sees it. I guess they would need their one arm would be up carrying the glove. There we go. So we can't move the baseball. We can move the outfielder who's trying to catch the fly ball. That's the idea. So you can move within the h1, h2 plane by tuning x1 and x2, but all we can do is get as close as we possibly can, which in this case would be to get under the ball, if that were to make sense. So that, once I saw this description of least squares, things started to really click for me. So I want to be clear here. The vector y does not lie in the plane formed by h1 and h2. We seek the closest point in the h1, h2 plane to y. So this, in this case, and you can maybe just see this from the diagram, by definition, the residual, which is the dotted line, is perpendicular to the plane. Because if we were at any other location and the residual was not perpendicular, it could have been shorter, right? That's the idea. So that's the shortest possible residual is the one that is perpendicular to the h1, h2 plane. And basically what we're trying to do is minimize the residual by making sure that it is perpendicular. And if we minimize the residual squared, I mean, that is basically it. We're trying to get the least possible squared error. That's where we get the term least squares from. So in this case, the residual, which would be written as y minus hx, is orthogonal to h. Okay, so in that case, we could say that h1 transpose y minus hx is 0, but also that h2 transpose y minus hx. Those are both 0. Okay, which makes sense, right? h1 and the residual are orthogonal. h2 and the residual are orthogonal. So we can actually simplify this and just say that h transpose y minus hx is equal to 0. Okay, let's distribute that. H transpose y minus h transpose hx is equal to 0. Okay, well, we can move something over the other side. I'm going to arrange it so that it looks like this. H transpose HX is equal to H transpose Y. Okay. And finally, I'm going to multiply both sides by H transpose H inverse. So to be H transpose H inverse H transpose HX equals H transpose H inverse H transpose Y. Everything over here is going to cancel out, so we'll just skip a step. And X is equal to H transpose H inverse H transpose Y. And this is it. You literally cannot draw enough red boxes around this equation. This is the least squares equation, which at this point, I don't even need to get, I would say that this is worth getting a tattoo over, but this will be tattooed on your mind by the time we're done with this course, definitely. This is the least squares equation. And what's interesting is this bit right here, H transpose H inverse H transpose, is the pseudo inverse. So before we just said, look, why don't we just take H inverse Y? Well, we've now proven geometrically that actually is the best possible way to solve this problem, given that this is our attempt. We're trying to kind of ignore the noise, not take that into account, then finding the value of X, which gives us the least squared error, is the least squares solution. So I want to just note one or two things, and then we will dismiss, because I know we're way over time today. One would arrive at this exact same solution by employing the techniques of optimization, which is why I borrowed the star notation. Those of you that have taken Dr. Hickens' design optimization, highly recommend that class. It's very useful for anybody. I mean, one of the most useful classes at RPI that I can possibly think of for somebody who's going into this field would be design optimization. It's very, very useful. And I borrowed his notation of using X star, right? Same idea. And so what we're trying to do here is minimize the sum of the squared error residuals. And that's where we get the term least squares. There we go. And we will actually, in the next lecture, employ some optimization techniques to look at some even fancier solutions to linear estimation problems. So when you've got a linear estimation problem, least squares is actually the simplest and kind of cheapest way to solve it, but there are better ways to solve it. So we're going to look at least squares, cooler older brother, weighted least squares, and then the even cooler, even older brother, maximum likelihood estimation. We're going to look at those in the next lecture. But for now, y'all have given me more than enough of your time. I appreciate you sticking with me for longer than we originally meant to go. It was very important to me that we had enough information to at least get a start on homework 2, specifically homework 2, problem 2 is now within your grasp. And actually, homework 2, problem 2, you can finish up with just a little bit further. Once we get to maximum likelihood estimation, which we certainly will by the end of next lecture, then you'll be in a good spot. And hopefully next time we'll also get to start batch estimation of measurements over time, which you need for homework 2, problem 1. But anyway, with that said, class is dismissed. I'm going to stick around at least until the top of the hour to answer any questions. But yeah, thank you for tagging along, everybody.